by dx is equal to you can apply this idea as long as you realize that this is really not a derivation of that formula, but it gives you a good, easy, safe way to get the formula. You have to keep in mind what this dy by dx means. It is actually a function expressing y as a function of x, and it is to be obtained from the implicit function. And dy by dx is not some dy divided by dx, it is the derivative of that function. Even though the method you use to obtain it gives that equation. Further, you have to always keep the invertibility condition in mind. This formula is really valid only if a certain condition is satisfied. All that if you keep in mind, then you can simply do this. We also saw another example for the chain rule, the different versions of the chain rule. So it's difficult to remember all versions. So for instance, one we had, I'll give you another example, E of the t, and then this was expressed in turn as a function of s and b to give E of sb. So again, I start with E as a function of b and t, so I can write the derivative or the differential of E as dE by dV at constant fixed temperature times dV plus dE by dT fixed volume times dT. Now you have to understand first that this, I want the derivative of B with respect to S and B, right? So that comes about by expressing T as a function of S and B. So I may replace the dt by the differential of T expressed as a function of S and B. Right? So then I would get dt by ds, fixed ds, plus dt by dp fixed s dv. It's a perfectly valid step. So now, this is what I want. So if you see now, right, there are two coefficients of dv. So if I gather together first the coefficients of dv, plus d by dt times dt by dt. That is the coefficient multiplying dv, right? Then I have to write the coefficient multiplying ds. That is simply ds. Now this is to be equated. Now I want E as a function of S and B. So dE, you have to remember, it depends on what variables E is expressed in terms of. Based on that, the differential will change. So I start out with E being expressed as a function of B and T alone. So I wrote the differential. Then I want E as a function of S and B. Then I recognize that that has to come by expressing T as a function of S and B. Obviously, final result should be corresponding to E expressed as a function of S and B, right? So this can be equated to E by ds. So now I simply equate the coefficients of dV and ds on both sides, and I'll get the formula that I wrote down by inspection by using the chain rule. So if you're a bit uncomfortable which version of the chain rule to use and how this would follow from the general formula of the chain rule where both variables were transformed into two other variables, might be sometimes confusing for you to infer the formula for a special case. We can always fall back on this method. Right? Only thing is important is it doesn't, so sometimes it's you just do it mechanically without understanding what you are doing. You will finally get the formula, but you should know what to do with it, under what conditions they apply and so on. Right? So that is important to keep in mind. For instance, another example I can give when I said that C is y minus mx, and then I wanted the derivative dc by dm. Right? So I went through the roundabout way deliberately so that you see what is involved, and I'll explain what is the different. You can two methods of getting the formula. One is certainly more roundabout than the other, but one that brings about clearly what is involved in the steps, or what do you require to be satisfied. First, the way we did it was, if I C has to be a function of m, if I start out with y being a function of x, that's what I have. I have to construct the function c expressed as a function of m, which is a derivative of y with respect to x. We've already defined it. M is dy by dx. If I want to really make sense of dc by dm, then I have to establish that c in fact can be expressed as a function of m. Right? So then the way I went about doing that is y is a function of x. So if y has to be expressed as a function of m, then x has to be expressed as a function of m. I don't know whether it's possible or not. We'll see that. Y is a function of x, which in turn, if I assume it can be expressed as a function of m, there is a condition involved. Right? You write the condition also down. And then I have minus m. And then again x. So I differentiated this, and then I got the result dc by dm is equal to minus x. We have already done it. I don't want to go through it again. Yes?
So, how can y and x can both can be a function of x?
Yeah, that's what we have to see. Both our functions can be expressed as functions of m. So, what I have here is m as a function of x, because y is given as a function of x. Right? And m is defined as dy by dx. So m clearly, once I differentiate y, take the derivative of that function, y hat, I will get m as a function of x. But that doesn't mean that x can be expressed as a function of m. We have already seen that. Right? So what is the condition for x to be expressed as a function of m? Dm by dx should not vanish. Right? Then, because I have from here m as a function of x, so if I want, what I want to be able to evaluate this derivative securely is x to be expressed as a function of m, and I know that if m is a function of x, it's not necessary that x has to be expressed as a function of m, right? So for that the condition, sufficient condition is dm by dx, the invertibility condition. Dm by dx must not vanish. Is effectively meaning the second derivative of y with respect to x should not vanish. That condition becomes very clear because I see that I have given only y as a function of x and directly m as a function of x, but to carry out this derivative, I need c as a function of m, which means x has to be expressed as a function of m, and I know that that's not always possible. So I find or write down at least that if this condition is satisfied, then I can do this. Right? On the contrary, if I were to employ the method of differential, right, this is a proper proof of this result. However, what I am going to write down now is a simpler way to get the final answer, but by no means can it be regarded as a proof. What I will do is, I simply take the differential of c. If I do that, dc, I can write the differential of c is dy minus mdx minus xdm. Right? And then I know that because dy by dx is m, the differential of y is mdx. So I cancel this and then I get dc equal to minus xdm. And then I write dc by dm is equal to minus x. So you don't have to be told, which is the easier method. Clearly this is much easier than this, right? But it sort of hides that there is a condition involved. It might be valid in most of the cases, but you can run into trouble. So at least you should be aware in the back of the mind when you're doing these manipulations, there are conditions which you might not really be paying attention to. So at least you know that if something goes wrong, you can go back and check what are the conditions you missed out. And it's possible that certain conditions are not satisfied where you are assuming they are satisfied, and that is why you're getting a certain problem, right? So normally textbooks don't worry about this condition. They just, you can write an entire monograph on the abuse of differentials in engineering textbooks in general and in thermodynamics textbooks in particular, right? I'm not going to do that, but you need to see the distinction between this. So now, what we need, as I pointed out, that you can regard the C defined as y minus mx as what is known as a Legendre transform, of y. No, but what we have is actually E as a function of S and B as a starting point. So we need the function of two variables. Now I'll generalize this procedure to point out that we can actually construct three, at least, Legendre transforms for y, which is a function of two variables. Suppose y is a function of two variables. The first function I can construct is, so there are two derivatives. M1 is dy by dx1 and M2 is dy by dx2. Two partial derivatives. Not just one m, but there are two derivatives. Right? They are partial derivatives. Right? So it's possible to show that there are three Legendre transforms we can construct. The first one I'll call as psi1, which is defined as y minus m1 x1. That's just like y minus mx here, but everything will be of the same form. Then I have psi2 as y minus m2 x2. Because there are two partial derivatives, so I can make m1 x1 and subtract it m2 x2. Let us see what happens when you do this. You can ask now what are the variables that psi1 would depend on, right? So for that I will adopt this, because now I have established that there are certain conditions available that you might have to find out, but I am not going to focus on those conditions. But I simply take the differential dy minus m1 dx1 minus x1 dm1. Right, just take a differential. Now dy I know is m1 dx1 plus m2 dx2, because it's now a function of two variables, right? That is what we have. Minus really, m1 dx1 will cancel out, and so I get d psi1 is equal to m2 dx2 minus x1 dm1. It is important to see, okay, the manipulations, are very straightforward, you can do it very efficiently. But it's important now to see what is the meaning of this. So what are the variables which psi1 is a function of? x2 and m1, right? So from this I can infer that psi1 is actually a function of m1 x2, right? And further, what is d psi1 by d m1? It is minus x1. That's what the differential equation is meaning. D psi1 by dx2 is equal to m2. So now if you compare it with this is the Legendre transform. So what have we done is we have eliminated x and introduced a new variable m here, right? So when I do y minus m1 x1, all I am doing is eliminating x1 and introducing m1, so that it becomes a function of m1 and x2 is retained as it is. Right? And you can see also the formula that corresponds to this is clearly this, very similar. So the derivative of the new function with respect to the new variable is simply negative of the variable that is eliminated, just as we have there. Now interestingly, the other derivative remains the same because we have dy by dx2, that's the variable that is retained, I don't touch that, is the same. So there's a pattern to this. I don't want you to remember the pattern, you can look at the pattern. Clearly, all you have to remember is this, y minus mx. That's the Legendre transform. Once I have this, then I can take the differential and easily figure out what are the formula of the derivative, what are the natural variables. Now clearly, if I do this, y minus m2 x2, then I get d sine 2 is dy, which is m2 m1 dx1 plus m2 dx2 minus m2 dx2 within brackets plus x2 dm2. Right? So m2 dx2 now will get cancelled. D sine 2 could be m1 dx1 minus x2 dm2, which now implies d sine 2 by dx1 is, which first means that sine 2 is now a function of x1 and m2. So when I do y minus m2 x2, the x2 gets eliminated and replaced by m2 in the new function. Right? You can see that pattern developing, and that is simply easy. If you are not sure of that, you all have to do this simple manipulation and you get that immediately. Right? So further, the derivatives, again the same pattern in the derivative of the variable that is retained remains the same, dy1 by dx1 m1, and the other one simply becomes the negative of the variable that is eliminated. Now there is another transform that can be constructed, because if you look at this, I have eliminated x1 and got m1. I can still eliminate x2 on top of that. Similarly, if I look at this, I have eliminated x2, right? I can still eliminate x1. Both will give the same result. So, or I can eliminate both x1 and x2 at one stroke, right? And I replace them by clearly m1 and m2, and it's very easy to now figure out how that would come. So I will erase this and do that here. So now I get another transform, which is defined as y minus m1 x1 minus m2 x2, and you can easily show then that d sine 1 2, right, would be what? Can you guess? What would be it a function of? It is clearly going to be a function of dm1, the differential. Psi 1 2 is now going to be a function of m1 and m2, because at both the variables which we eliminated, we will easily verify that this would be minus x1 dm1, and this would be minus x2 dm2. You can also clearly write psi 1 2 as psi 1 minus m2 x2, or as psi 2 minus m1 x1. Whenever I do this mx precedence, I eliminate one variable and replace it by another. Right? So I have reached psi 1, and then that is a function of, right, m1 x2. By doing m2 x2, I eliminate x2 and get to psi 1 2, which is a function of m1 and m2. Or I can do this psi 2, and when psi 2 is a function of x1 m2, right? And so when I do this, I eliminate x1 also, and I get psi 1 2, which is a function of m1 m2. Right? So I'll write it more clearly in the case where we want, that is the thermodynamic functions. Right? So clearly, I start with E equal to, and dE is PdS minus PdV. So if you remember this basic equation, by recognizing the other functions that I am going to write down are got by successive Legendre transformation, you can easily write down the rest. Right? So first, I will eliminate S, right? So I'll put minus S, that is I'm eliminating S from here. So that has to be clearly related to E by ds, which is P, right? So that function is A, it is E minus ds. So it's minus of the variable and eliminating times the derivative of the original function with respect to the variable that I am eliminating. Y minus mx is all you have to remember. But now you have more than one variable. You can have y minus m1, x1, m2, x2, and various other combinations also, right? As we have seen. Y is a minus m1, x1 is what I am writing. Right? Then you can easily show that dA is minus SdB, right? Minus BdB. Okay, this minus BdB is not affected at all. This is simply because the negative of the variable that is eliminated. You see the same pattern, right? Then you will have now I'm going to eliminate B, right? So what should be the function? E minus B times the derivative of E with respect to B, right? Now that derivative will be minus B. So the function actually would be H, which is equal to E plus B. E minus B times D. Right? So what is there in the minus is very important. Right? It's not E plus PS is not a Legendre transform. Only E minus PS. You have to be very careful about the sign. Y minus mx is what you have to understand. Here the m, that is m2, is actually minus p. So obviously that would lead to E plus dB. You can easily, by taking the differential, express this is dx equal to, right, dds plus b dp. Of course, if I were to write it in the strict terms, I would have to write it as minus b times d of minus p. But I don't want to do it because we know pressure is a variable. We don't want to replace it by minus p. Strictly, if I have to follow this, so I will simply write it as plus b dp. And instead of minus p, I am using p as a variable. But here I have to be very careful. Obviously, e plus db. Right? So that's what. So clearly, the definition, this is specific Helmholtz free energy. This is clearly a function of T and B, and this is the specific enthalpy, as you might have already been introduced. That is a function of S and P. Right? And then there are three ways in which I can obtain the class function. So if I start with H as S and P, and now I eliminate minus S. So clearly I'm going to get t and p as a new variable. So I get the new function g, which will be a function of tp, right? And g is equal to h minus the variable I'm going to eliminate is s, and the derivative of h with respect to s is t, so minus ts, and you can easily show that dg minus s dt plus v dt. On the other hand, I can also get the same g from a is a function of t and p, right? And I can now eliminate v, right? And so if I eliminate v, then g is a, right, minus the variable I am eliminating v times the derivative of a with respect to the variable I am eliminating, which is minus v. So again, it will be a plus bb, and you will get the same expression. That won't change. On the other hand, I can eliminate both the variables s and p at the same time, minus s minus p, right? So g now would be the psi 1 2. I've shown three ways in which to obtain psi 1 2, either from psi 1 or psi 2 or directly from 1. Okay? By eliminating both of them simultaneously, then I will have y minus m1 x1 minus m2 x2. That would be e minus ps plus pb. And again, dg would be given by the same equation as a function of t and p. Right? Are there any questions? So now I can write the whole set of relations in the following way, combine all of them. So I have, let's write it here, dE by ds is at constant t is t, and dE by dv at constant s is minus p. I'm just writing from the differential. I'm writing what the derivative is. That's what the differential means, right? And so dA by dE at constant t is minus s, and dA by dE constant t is minus p. Again, dH by ds at constant p is p, and dH by dP at constant s is dV. All of this can be written by inspection. Again, dG by dE at constant t is minus s, and dG by dP constant t is p. So for each one of these, I can write the so-called Maxwell relations, which are simply arising out of the fact that the mixed second order derivatives are equal. Okay? So the first case, the condition that leads to the Maxwell's relation, the mixed second order derivatives of E with respect to S and P are equal. Right? So I can write EBS is equal to ESP. Right? So from that I can write dP by dV at S is minus dP by DC. Equation will be very useful. DC later on, what is the purpose of doing all this? Where these functions are important and what to do with them. Right now we are just focusing on the basic properties. See later on how they are used and why we need actually so many of these functions. And finally, secondly, ADE is equal to ADB, from which both of them have negative signs. So I can write this as ds by dt at t is dp by dt at t. This is in fact a major discovery of classical thermodynamics. One of the properties of S we saw, the derivative with respect to d, if you recall the earlier equations we looked at from Carnot and George's equations, was that ds by dt is dt by dt at b. Then the third Maxwell relation is HES equal to HSP, which would imply that dt by dp at S is equal to dp by ds at B. And then the fourth is HGBE is equal to GEP, which implies that minus ds by dp at D is dp by dt at B. These are what are known as the Maxwell's relations. You can see, if you know how to construct, this is the basic thing that you have to remember. If you know how to construct each one of the functions, this is of course called as the Gibbs field. This is a specific Gibbs free energy. Even though essentially Gibbs is the one who introduced all of these functions, but obviously you cannot call everything then in thermodynamics will become Gibbs, and so we have to give other names also. So this is how conventionally they are denoted terminology. That's why it's called as G, Gibbs free energy. Of course, H is enthalpy, you cannot confuse it with the Helmholtz. I'm just following the convention followed in the majority of the textbooks. So we have this, these are the Maxwell's relations. So as long as you recognize the y minus mx is what is going to give you the three Legendre transforms. There are three different ways of writing the y minus mx. It's y minus m1 x1, y minus m2 x2, and y minus m1 x1 minus m2 x2. You can get all of these by simple manipulation. And then by invoking the equality of the mixed partial derivatives, you can write down the Maxwell's equation. Should not take more than 5 minutes for you. Right? So this is what it is, and among these, probably these two will have the most significance. Right? So right now we have a bad idea to remember them, but they are coming from A and G, two most important, widely used Maxwell's relation. So now, what do we do with this? Right? So that is the first question. But what you should understand that even though these are fundamental equations, E expressed of these clearly these two would probably be the most directly useful in that the variables T and P are probably the most convenient to use in actual practice, or T and B. Right? But however, when you look at the fundamental equation, these has S and P and this is S and P. What we would like to do is actually express all the functions, the derivatives in terms of T and P or T and P. That's what will be useful practically. So I will now set 4. The basic objective would be, right, the jumping from one equilibrium state to another. One equilibrium state to another. We don't really worry about it. Obviously, have to undergo a certain process, right? Because equilibrium means it is fixed. So if you leave it as it is, don't change the conditions. It's going to remain as it is. Right? But in actual practice, we are interested in changes in properties which take place between two states. Now, if these two states turn out to be equilibrium states, then we can use these equations to calculate the properties of those states and also the changes. Right? So, that is what we would like to do. So, let us say a common specification of the states are through its temperature and pressure. Most common specification. The gas expands from a certain temperature and a certain pressure. So some temperature and pressure. The most common specification. So what we would like to do is calculate the changes in, let's say, each one of these properties. Let's say delta E of T2, T2 minus E of T1, T1, delta A, delta T, and so on. Why are these functions important? I'll give you just one simple example, it's very easy to derive, right? So, suppose let's consider the first law, dE by dt is equal to 2r minus w of. So, one instance where these differences might be important to calculate is we consider a system undergoing a process from one equilibrium state to another, and these quantities we will show all have relevance in different types of processes. Simplest is the adiabatic process. Right? So we now consider the adiabatic process. U are 0. Now I integrate this over time. So the first law has no restriction on whether you are considering reversible process or irreversible process. Valid for all processes. So but the crucial point here is I am considering only the adiabatic process, which QR is 0. So what I get is that delta E, which is the change, this is T, is the time, right? Let us say it is now going from one equilibrium state to another, right? So delta E is minus W. What this means then is W is equal to minus delta E. So what you have to see the significance of this. Normally, when you're talking about work done, only case where you might have probably calculated the work explicitly is when the body undergoes a reversible process. Then you can simply do PdV. Even that you have done for some special cases like an adiabatic process or an isothermal process. Otherwise, calculating the line integral will not be that easy, right? However, what this says is it doesn't matter what process it has undergone from one to another. It might have undergone a completely irreversible process, but this formula is still valid. This formula is valid even if the states are not equilibrium states. However, to calculate this difference, right? If the states happen to be equilibrium states, what this means is that I can get the work done in an adiabatic process without worrying about whether it's reversible or not, right? By simply calculating the change in internal energy between the two states. Now, since I have some information about the internal energy, right? When it corresponds to equilibrium, because all these relations correspond to only equilibrium states. So if my end and initial points are equilibrium states, then I have a chance of calculating, even if the process were irreversible, calculating the work done by simply calculating the difference in energy between the two equilibrium states. Right? That is what we will take up. You take up an arbitrary property, can be A, E, S, whatever you want, right? Take an arbitrary property denoted by U. Now, if I want to calculate the change, now I say that it is T1, P1 and T2, P2. Undergoes a process. I don't now care about. I've been later on introduced where I'll give you one example where the internal energy change will be related to the work. You can give examples for other quantities also of the changes, would mean where they would be used. Helmholtz free energy or the enthalpy, where they are used. So now I want to calculate delta U, which I am defining as U of T2 P2 minus U of T1 these are state functions. To calculate the difference, I will integrate. I have to integrate actually from point 1 to point 2 du by dt at p dt plus du by dt at p dt. Because u is a function of two variables. So if we want to calculate the difference in function, then I can choose any path. That is a convenience I have now. Using any path between the states 1 and 2, that we will see what are the best paths to choose. What I want to now point out is that what will enter into that formula are the derivatives of u with respect to t and p. Right? Now, sometimes it's also convenient to integrate in the dv domain. So we may want to also calculate it as b, and you see why that is the case. Right? So what we want now, I want you to understand that what we require are derivatives of u with respect to t, both with pressure kept constant or volume, specific volume kept constant, and the derivatives of any property u with respect to b and t. B and t, right? So now you see here that when you are looking at g, its natural variables are t and p. So automatically the fundamental equation, the general equation will give those values. Similarly, if you look at a, its natural values are t and p, so automatically get what the derivatives are. For instance, if I replace u by a here, then I know exactly what the two quantities are from those equations. Similarly, if I replace it by g, then in this integration I know what the derivatives are. However, E and H, for instance, their natural variables, that is the variables in the fundamental equation, are not B and T or T and P, but S and D and S and B. So what we want is those functions also, we want the derivatives with respect to only T, P and B, because that's practically that is what we need to do. Normally when especially we don't see the body move from one entropy value to another entropy, we don't even know what the entropy is. But we can easily say body expands from certain temperature especially to some other temperature especially, or some other from temperature and volume to another temperature and volume. Right? That is more easy to practically that is what you need to specify. So what now the problem will take up is how to calculate the derivatives of each one of these quantities, and even though S is not appearing as a dependent variable here, we would like to also calculate the entropy changes. That will also be very important in many cases. Right? So what we want, we see where these differences are actually useful, but for now you should be convinced that these derivatives will be useful to have. Right? So that is the first problem that we will take up. So we will be starting from these basic equations. We want to calculate one by one what are the derivatives of each one of these quantities, and we will take up E, S, H, A and G. We want to calculate for each one of them, we want to consider them as functions of B and T or P and T, and calculate the corresponding derivatives and see how to obtain those derivatives. That is what we will take up now. Are there any questions? If not, we'll meet again tomorrow and continue.